So let's talk about the electron volt. Now the electron volt, well, let's go back to a volt. If we remember when we're talking on the macro scale, 1 volt is equal to 1 joule per coulomb. Now, when we're talking about individual atoms or even individual electrons, 1 joule is a huge amount of energy. I mean, normally we're talking about like 10 to negative 19 joules when we're talking energy for an electron, for the energy for a single electron. So the easiest way to think about the electron volt is if at 1 volt, how much energy does each electron have? Each electron have. And well, we can try this out. Well, what we'd actually do is we'd actually take into account the amount of number of atoms or electrons in a coulomb. So 1 electron volt equals 1 joule divided by 1 coulomb, which is equal to 1 joule divided by 6.242, or however many times 10 to the 18 electrons, which are in a, just check, which are in a coulomb, which is going to equal, let's just make sure we got this right, 1 divided by 6.242 x 18 electrons is equal to 1.602 times 10 to the negative 19 joules. So this is how much each individual electron is going to have. This, by the way, was also exercise 8.1. So an electron volt basically tells us, yeah, how much zip does an electron have? If we're hitting stuff with light, it's going to have, I don't know, 1 to 5 electron volts or something like that. High energy stuff, high energy waves get up to like hundreds, if not thousands. When you're getting into atomic energy, then your atomic particles can have millions or even hundreds of millions of electron volts. So, but even 100 million electron volts is still only a very small fraction of a joule. So let's actually try exercise 8.2. And now this question says visible light is going to be in the range of 400 nanometers, which is going to be your blue, to 700 nanometers. Well, actually I've got to about 880, but that's going to be much more reddish. How many electron volts? How many electron volts for each photon at that range? How much? So each photon is going to have how much energy? Well, we know that E equals HF. That's cool. But on your sheet it gives H is equal to 6.626 times 10 to the negative 34 joule seconds. For this, we want to know how many electron volts. So we're going to have, let's convert H, Planck's constant, into electron volts. So to do that, we can go H is equal to 6.626 times 10 to the negative, 34, isn't it? 10 to the negative 34 joule seconds, and we divide that by the elementary charge, 1.602 times 10 to the negative 19. Negative 19, what's that? That's, coulombs, equals, so this is time to stick in the calculator, 6.626 exp negative 34 divided by 1.602 exp negative 14 equals 4.136 times 10. It does not seem right. 6.626 x negative 34 divided by 1.602 x negative 19 equals 4.136 times 10 to the negative 15 electron volt seconds. Because remember, we're changing the joules to electron volts, but we're still going to keep the seconds. So in this case, E is going to equal 4.136 times 10 to the negative 15 electron volt seconds times whatever the frequency is. And so next question is, what's the frequency? So for red light, first thing we have to do is work out what the frequency is. So frequency is going to equal the velocity over lambda. Velocity for light is 2.998 times 10 to the 8 meters per second. That's the speed of light in a vacuum. Divided by the wavelength of the red light is going to be 700 nanometers, so that's 10 to the negative 9 meters. And again, we stick that into the calculator, 2.998 x 8 divided by 700 x negative 9 equals 4.283 times 10 to the 14 hertz. And that seems a reasonable number. Light, visible light is in the range of 10 to the 14 hertz, so that seems quite reasonable. So we now stick this into the equation, E equals HF, which is equal to, well, we worked out H over here, 4.136 times 10 to the negative 15 electron volt seconds times frequency is going to be 4.283 times 10 to the 14 hertz. Stick that all in the calculator. Times 4.136 x negative 15 equals 1.77 electron volts. 1.771 electron volts. 1.771 electron volts. And does that seem reasonable? Yeah, I mean, light's usually in the range between about 1 to 10 electron volts, so that seems perfectly reasonable to me. So now we're going to repeat this again for blue light. So we've got the same thing. F is equal to 2.998 times 10 to the 8 meters per second. Divide that by the wavelength, so that's going to be 400 nanometers, so 400 times 10 to the negative 9 meters. So remember, always convert to kilograms and meters per second, and that's going to equal, so let's stick that out there, 2.998 x 8 divided by 400 exponential negative 9 is equal to 7.495 times 10 to the 14 hertz. So yep, again, that seems reasonable because it's to the power of 14 hertz. And let's put this over here. So energy is going to equal HF, which is going to equal 4.136 times 10 to the negative 15 electron volt seconds times the frequency, which is 7.495 times 10 to the 14 hertz, times 4.136 x negative 15 equals, does that seem about right? Yep, 3.09, let's call it 3.100 electron volts. And yes, that does seem reasonable to me. Again, this is, I mean, one of the questions you should always be asking is, does this seem reasonable? With experience, yes, that says that is actually quite reasonable. So let's actually try this on 8.3. This will also give us a chance, exercise 8.3, this will also give us a chance to do a problem using photoelectric effect and cutoff frequency. So we have a light frequency, 2 times 10 to the 15 hertz. Okay, so remember, visible light is usually in the 2 times 14 hertz range. So 2 times 10 to the 15 hertz range is actually going to be ultraviolet light. It's shone on an aluminium surface with a work function, shone on metal, aluminium. It's got a work function of phi is equal to 4.08 electron volts. So remember, this photon must supply this much energy before it can even knock an atom loose, or electron loose, sorry, knock an electron loose. What is the maximum? It's the maximum kinetic energy. Maximum kinetic energy, okay, value. So, of the electron volt. Okay, so we're going to use the function equation we had earlier. K is equal to HF minus phi. So we want to find this. Do we know what H is? Yeah, well, the whole point of H is it's a constant, and we worked it out earlier that H was equal to 4.136 times 10 to the negative 15 electron volt seconds. Do we know what F is? Yeah, we're given F. Do we know? And the answer to that, when we multiply those together, will give us an answer electron volts, because we're using the electron volts but minus, and we have the value there, so let's just plug in the number time. So H is going to be 4.136 times 10 to the negative 15 electron volt seconds times the frequency, which was up here, 2 times 10 to the 15 hertz. So that's the actual amount of energy in the photon. I mean, if we were to draw a picture, here's our piece of metal, we have a photon coming in here, hits this, knocks off an electron, and that goes sailing off. So that's the amount of energy minus the energy of the work function, 4.08 electron volts. So if we work out this bit here, so 4.136 x negative 15, I cannot stress to you the value of that key there, the exponential key. Saves a whole lot of typing times 10 to the power of, and yeah, has other functions as well, times 2x15. The other function is that means we don't have to keep drawing numbers around these, put brackets around these. So the amount of energy this photon has here is going to be 8.272 electron volts minus 4.08 electron volts. So it's the amount of energy, the maximum amount of energy this photon is going to have is it's going to have 4.192 electron volts max. So it's going to be the maximum value. Cool. So the next question is, what is the cutoff frequency going to be? What is the cutoff frequency? So the cutoff frequency, sorry about that bad T. For cutoff frequency is the lowest frequency that will knock an electron off. So if we rearrange, so if we have K is equal to HF minus phi, frequency cutoff is when K equals 0. So when this has 0 kinetic energy, that's going to be the absolute when that's exactly equal to 0, that's going to be the lowest amount of energy. Anything more than that, and it's going to knock an electron off. So HF minus phi, so we rearrange that. Phi is going to equal HF. Well, we know this value. So we're going to rearrange for F. So rearranging for F, F is equal to phi over H. We know the value of the work function up there, 4.08 electron volts. We worked out earlier what H is going to be in electron volts, 4.136 times 10 to the negative 15 electron volt seconds. So that's going to give us an answer of, let's work it out, 4.08 divided by 4.13 exp negative 15 equals, this can't be right, Australian, 4.08 divided by 4.136 exponential negative 15 equals, that looks better, 9.865 times 10 to the 14 hertz. So that's still going to be ultraviolet, but it's going to be soft ultraviolet. But hopefully you'd also notice what happened there. I got an answer for this. The very first thing I'm going is, no, that doesn't actually seem reasonable to me. So I went and rechecked. If an answer does not seem reasonable to you, one of the first things you should do is recheck your math, check your calculator technique, and then have a quick look to make sure your working was right. So remember, one of the first things to do is always ask, does this question seem reasonable? 9.865 times 10 to the 14 times 10 to the 14 hertz for cutoff frequency for aluminium seems perfectly reasonable.